In this video, we're going to discuss section 1.1, in which we provide some key definitions and discuss some terminology that's going to allow us to categorize differential equations so that we can apply the appropriate solution technique. On the first page of the notes, I have just a couple paragraphs emphasizing the importance of this terminology. As you'll see soon, there's specific solution techniques which require the differential equation to have a very specific structure. And so a key first step in every problem that we're going to do moving forward this semester is to identify characteristics of the differential equation that we're presented with in order to be able to properly determine which solution technique is appropriate for that differential equation. Let's go ahead and get started with these definitions. I'll also just remind you that this aligns with section 1.1 in our textbook. And so if you want extra explanation or to see a few more examples, I'd encourage you to go look at section 1.1 of our textbook. The first definition is of what a differential equation is. That's what this course is about. So what is a differential equation? Simply put, a differential equation is any equation which contains a derivative. Pretty straightforward. I like to add that it usually contains some unknown function. So there's actually a function which we don't know an explicit expression for, and that function is involved in the differential equation somehow, along with at least one of the derivatives of that unknown function. We'll see some examples in a sec. We're going to define the order of a differential equation to be the highest derivative that's present in the differential equation. So if my differential equation has a second derivative, then we'll say that that's a second order differential equation. The next definition here contrasts what are called ordinary differential equations versus partial differential equations. Definition's a little wordy. Let me try to explain. An ordinary differential equation involves functions of one independent variable. That is, these are classic Calc 1 functions. So this is an f of x, a h of t. My function has a single independent variable. Therefore, all of the derivatives are ordinary derivatives, just regular Calc 1 derivatives. In contrast, we could potentially have a differential equation which involves derivatives that are partial derivatives. Partial derivatives are derivatives of functions that have multiple independent variables. Here at NAU, we don't talk about functions with multiple independent variables until Calc 3. And so maybe you've recently taken Calc 3. If you're currently enrolled in Calc 3, you haven't talked about partial derivatives yet. The good news is, for the purposes of this course, we're going to focus on this first type, ordinary differential equations. We'll hopefully get to talking about partial differential equations a little bit at the end of the semester, but for the most part, we're just going to focus on ordinary differential equations. And then I just want to highlight the terminology. You've heard these terms, ODE and PDE. Those are simply referencing these two different types or categories of differential equations, ordinary differential equations or partial differential equations. So let's take a look at an example where we apply the terms that we have just defined. This is example 1. I have several differential equations. What I'm asked to do is I'm asked to state the order of the differential equation and then determine whether the differential equation is ordinary or partial. Let's take a look at this first one. I have a dH/dt, so I recognize that that's a derivative term. That's a first derivative term. I have natural log of t. I have h of t, which is an unknown function. I don't know what h of t is, and yet this equation involves h of t along with its own derivative. So this is a classic differential equation. I also have t squared, sine of t. Looks like t is my independent variable in this equation. And my derivative, the only derivative involved is this dH dt, which is a first derivative. So that means that the order of this differential equation is a first order, or we'll write here order equals 1. And then the function involved is an h of t. So the unknown function is h of t here. That's a classic Calc 1 function where I've just got a single independent variable. So I would categorize this as an ordinary. I'll probably write ODE in the subsequent examples. There's lots of other important properties that we'll identify of these types of differential equations, but for the purposes of this example, those are the two properties that we want to look at. Let's move on to the next one. Here I've got y double prime minus y prime minus 2y equals e to the negative t. It's a little unclear from the statement of the problem, but the dependent variable is this y. And the independent variable, it doesn't say explicitly. Notice in the previous example, we had h of t. So I knew clearly what the independent variable was. In part B, it doesn't clearly state y of x, y of t, y. But from the context, I do notice a t that shows up in the differential equation. So I can infer that t is the independent variable. Y here then is my dependent variable, my unknown function. And it looks like the highest derivative that I have present is this y double prime. So I would say the order equals 2. And since I only have this single independent variable, also since I've got these primes, again, I don't know how much you would have emphasized this in your Calc 3 class, but when you're taking partial derivatives, you cannot write those derivatives as primes. So the fact that I've got a prime here indicates that this is an ordinary derivative. So I'll label this one O. D. Let's take a look at part C. Here I've got sine of pi t times the derivative of u with respect to x minus the derivative of u with respect to t. So here, from this notation, I can infer that I've got a dependent variable u, and that dependent variable depends on x, and it also depends on t. I'm going to note that kind of out here in the margin that my function is a function u with two independent variables, x and t. That's also indicated by these funny d's. Notice that in part A, we've got a sort of classic Roman d. Down here in part C, we've got these funny ones, these deltas. That indicates that this is a partial derivative. So I guess I'm getting ahead of myself here. I guess I've already identified that this is a partial differential equation, or a PDE. And that's because the function is a function of multiple variables. Two independent variables. How about the order? Du dx is a first order derivative. Du dt is a first order derivative. They're different derivatives, but they're both just first order. So in that case, my order equals 1. Let's move on to part D. Again, the notation is a little ambiguous, and this will be true of a lot of the examples that we see this semester. So we have to kind of infer from the notation some properties of the functions and variables involved. Here I've got an f sub xx. That notation is equivalent to this partial derivative notation, except that I've taken the second derivative with respect to x. This f sub x is equivalent to the partial derivative of f with respect to x. This would then be the partial derivative of f. Okay, so I've said partial 7 times already. So clearly this is a partial differential equation, or a PDE. And again, just to clarify the structure, it looks like I have a function f, and that function is dependent on x and y. There are two independent variables, x and y. This expression on the right is then just an expression in terms of those independent variables. So we've identified that we have a second order derivative, so the order of this differential equation will be 2. So we've seen a couple ordinary differential equations, a couple partial differential equations. Part E has y prime equal to 1 minus 2x y double prime. I've got a second derivative, and my derivatives are primes, so that indicates that the unknown function y must be a function of one independent variable. So I can label this as an ordinary differential equation. I actually want to go ahead and explicitly indicate here that my function y appears to be the function of x. Let me go ahead and state that for these first two. We decided up here that the h of t was given to us explicitly, so I knew the structure of the dependent and independent variable in that case. On part B, we decided that we had y being defined as a function of t. Again, I mention that because this structure is not always stated explicitly in the equation, so sometimes it takes a little work to infer this structure. All right, a couple more. Part F, got a first derivative. The derivative is being squared. And then I've got this unknown function y again. Since the first derivative is the only derivative present in this differential equation, I have order equals 1. And since we have an ordinary derivative as indicated by this prime, that tells me that my unknown function y is a function of a single variable. So we're dealing with an ordinary differential equation. And as with the previous example, the structure here is that my dependent variable y is defined as a function of x. Part G, I clearly see that my derivative is first order, and this is an ordinary derivative. because it's a derivative with respect to t. These p's must therefore be functions of t. Oh, this is the example that we used in the previous lecture. We tried to find the inflection points of this. And so this is a differential equation. So even in that first lecture, we were dealing with the differential equation, even though we hadn't defined it yet. This is an ordinary differential equation. And just to clarify, this structure is a little bit more explicit, but I do have a function p being defined in terms of the independent variable t. One last example, looks like y is my dependent variable. I've got a y double prime. This notation, I'm not sure if you're familiar with this, but if you see in the exponent, there's parentheses around the number, that's indicating the fourth derivative. So I know that this is an order 4 ordinary differential equation. And just to clarify the structure, it once again looks like I have y as my dependent variable and t as my independent variable. Let's move on to the next definition. At the top of page 2, definition 2 provides a category of differential equations which is extremely important. This definition is a little strange, and in the past I found it takes students a while to get accustomed to this definition, but this is really, really crucial. This category or this class of differential equations is very important. These are called linear differential equations. Linear, the term linear can be applied to ODEs or PDEs. And my definition is a little different than what the book says. My definition is a differential equation is called linear if all dependent variable and derivative terms are linear. And by linear, I mean raised to the first power. So to emphasize, I need to look at the dependent variable terms. So if I've got y as my dependent variable, I have to identify my dependent variable terms. I also have to identify any and all derivative terms. So I'm going to look for dependent variable terms and derivative terms, and then I'm going to ask, are those linear? Notice that this definition puts no restriction on the independent variable. I'm simply asking if the dependent variable and its derivatives are linear, raised to the first power. Let's take a look at an example. These are the exact same differential equations we just looked at in example 1, but now we're just asked to identify whether they're linear or not. What I'm actually going to do is I'm going to go through, and in each equation I'm going to highlight the key terms that we're focusing on. This is a derivative term, so that's one of the terms that we're focusing on. Here's a dependent variable term. Now those highlighted terms, this dh dt is just to the first power. This h of t is just to the first power. So those satisfy the definition, so this is linear. You might look at this and say, well, wait a second, what about that t squared? T squared is not linear. Sine of t is not linear. Natural log of t is not linear. But remember that this definition only focuses on the dependent variable terms and derivative terms. So the independent variable terms, that is terms that involve just t in this case, can have any form. There's no restriction on those at all. Let's take a look at part B. Let's try to highlight my dependent variable we said was y. So then we've got a derivative term of y prime, derivative term of y double prime. I do have a nonlinear term, e to the negative t, but that's nonlinear in the independent variable. And so that there's no restriction on the independent variable. So these dependent variable and derivative terms are linear. Therefore, this differential equation is linear. Hopefully you're starting to get a hang of it. In part C, remember we said that the dependent variable was u, and the independent variables were x and t. So this partial of u with respect to x is a derivative term. This partial of u with respect to t is a derivative term. Having a hard time with my highlighter here. You get the idea. These two derivative terms are the only terms that I'm going to focus on when I'm trying to determine linearity. Since both of them are raised to the first power, this differential equation does qualify as being linear. Part D, I have a derivative term, another derivative term, another derivative term. Here we have to be careful because the y in this equation is an independent variable, so I'm not going to highlight it because it's not one of the terms that I'm focusing on in order to determine linearity. And all of my dependent variable and derivative terms are to the first power, so this does count as linear. How about part E? I've got a y prime term to the first power, so far so good. I've got a y, and then I've got a y double prime. Notice that these two are multiplied together. Since those two are multiplied together, we think of that combined term as having a sort of combined degree of 2. So that combined term where I have dependent variable multiplied by one of its derivatives violates the restriction that every term of interest be to the first power. So this is an example of a nonlinear differential equation. Let's take a look at part F. Part F has a derivative term being squared. So that pretty clearly violates that restriction, so we can determine that this is also nonlinear. Let me highlight the other terms of interest in part F just for consistency. How about part G? On the left-hand side, I have this derivative. Again, I'm thinking of this as one term, so that's a derivative term. Here I have p, which is being raised to the first power, and then I have another p, which is being raised to the first power. So it's tempting to say that this is linear, but notice that on the right-hand side, if I was to FOIL out or distribute this coefficient term, then these p's would be to the second power, and so this is in fact nonlinear. And lastly, in part H, my derivative terms, or my terms of interest here are y. This is, again, not the fourth power of y, this is the fourth derivative. So I didn't write, triple prime, or I guess in this case quadruple prime, but this is just the fourth derivative. Here's y double prime, here's y. The independent variables, t, ln of t, I'm not concerned when I am trying to determine linearity. So each of these derivative and dependent variable terms is to the first power, so this counts as being linear. Again, please take a second to review these examples because this notion of linearity is really crucial, and so that's one that we're going to need to rely on several times throughout the coming semester. Let's take a look at the next definition. In definition 3, I said at the beginning of these notes that our goal is to find the solution of a differential equation. So what exactly is a solution? If I'm dealing with an algebraic equation, the solution is a number. I might start with 2x equals 4, and then my solution is x equals 2. We're dealing with a different type of equation, so I expect that the solution will be something different. In this case, a solution is any function which satisfies the differential equation. What I mean by satisfies the differential equation is if you take the function and the appropriate derivatives and plug it into the differential equation turns out to be true. Let's take a look at an example of that. In example 3, we're told to verify that y equals sine of 2t is a solution of the ODE, ordinary differential equation, y double prime plus 4y equals 0. So, just to have these for reference, my differential equation is y double prime plus 4y equals 0. Somehow, I have come up with a solution. I have not, in this example, explained how I generated this solution, but you're going to trust me that we're going to verify that this is in fact a solution. So what that means is I'm going to take the function itself, which in this case is y equals sine of 2t, and then I'm going to look at my differential equation and I'm going to ask, what do I need to plug in? I need to plug in a y right there, so I'll plug that in. I also need to plug in y double prime. To get y double prime, I'm first going to need to calculate y prime. That gives me 2 cos of 2t. And I have y double prime equals negative 4 sine of 2t. So I have derived all of the ingredients that are required by my differential equation. I can now take those ingredients and plug them in the appropriate places. I'll take y double prime, plug it in there. I'll take y itself and plug it in there. And I'm going to verify that this equation does hold. So plugging in y double prime gives me negative 4 sine of 2t plus 4 times my y, which is sine of 2t. And sure enough, those do cancel each other out, and so this differential equation is true. So to use our terminology, we have just verified that the given function is a solution of the given differential equation. Beneath example 3, I have a paragraph pointing out a couple important details. I note that if we were to try y equals 2 sine of 2t, it would also satisfy this differential equation. In fact, so would y equals 3 cosine of 2t, y equals negative cosine of 2t, and y equals negative sine of 2t plus cosine of 2t. This demonstrates the fact that a given differential equation potentially has lots and lots of solutions. In fact, most differential equations have infinitely many solutions. When that's true, our goal becomes to identify a family of functions. So instead of expecting to find a single function, which is the solution of my differential equation, I'm actually interested in finding a family of functions, all of which are solutions individually to the given differential equation. And when we do that, we call that family of functions the general solution of the differential equation. Let's go ahead and move on to the next definition. Definition 4 introduces what are called initial conditions. Initial conditions are specific numerical values that are typically given as input-output pairs that must be satisfied by a solution of the given differential equation. So what initial conditions do is effectively pick out a specific solution with the stated given properties. We've said already that typically we'll start by having an infinite family of solutions, a general solution. So what initial conditions do is they allow us to select one specific solution from that infinite family. I typically will refer to this as a particular solution. That's not the best term, and I'll sort of explain why later in the semester. Our author calls this an actual solution of the differential equation. So just to clarify, I have two little paragraphs here that I hope that you will refer to throughout the rest of the semester and just kind of understanding what the expectation is for a specific problem. So the first paragraph says, if no initial conditions are provided, our goal is to find a general solution. So let's just clarify, no initial conditions means general solution. A general solution, we'll see an example in just a second. A general solution will usually be an expression that contains one or more unknown constants, because again, it's defining an infinite family of functions as opposed to one specific function. If initial conditions are provided in a particular problem, then our goal is to incorporate those initial conditions mathematically so that we solve for the unknown constants. So in this case, instead of trying to find the general solution, we're going to solve for the unknown constants algebraically in order to have a particular solution, or as our author calls it, an actual solution. And then one more piece of terminology. In this second case, when we are provided with initial conditions, sometimes the problem is referred to as an initial value problem, or IVP. Let's take a look at the next example. In example 4, we're actually going to revisit the same differential equation from the previous example. Y double prime plus 4y equals 0. And we're told that the general solution is y equals a constant times sine of 2t, plus another constant times cosine of 2t. At this point, I have not explained how I generated this general solution. So you're going to have to trust me that this is the general solution. Pretty soon, we'll talk about the methodology to derive this general solution ourselves. But for now, we're going to trust that this is the general solution. And notice that as predicted, this general solution has unknown constants. I don't know what C1 and C2 are. And if you were asked, say, to graph this function, well, you'd have infinitely many functions to graph because you need to graph all possibilities for the two unknown constants C1 and C2. So this is a general solution because it is an infinite family of solutions. In addition to the differential equation, we are provided with a couple input-output pairs. Specifically here we have if t equals 0 in the original function, then the output should be 0. If t equals 0 in the derivative, then the output should be 3. Those are my initial conditions. So in this particular problem, we are provided with initial conditions. So using the term that I just defined, this particular problem would be an example of an IVP. This would be an example of an initial value problem. So what we want to do in this problem is to mathematically incorporate these initial conditions in order to be able to solve for the unknown constants that exist in my general solution. So let's think about how we could do that. I have y here, And this equation tells me that remember, this is the independent variable. So if I plug in t equals 0, then the output should be 0. Let's go ahead and do that. Let's take my general solution and let's plug in t equals 0. So that gives me c1 sine of 2 times 0 plus cosine of 2 times 0. I can simplify that. And then this output, when I plug in t equals 0, we're told that the output value should be 0. So I can plug in that value here on the left. Now, if you remember from the unit circle, sine of 0 equals 0. Cosine of 0 equals 1. So simplifying this a little bit further. So that tells me that C2, the second unknown constant in my general solution, in this particular case is going to be 0. So in my particular solution, I'll actually plug in the coefficient of C2 equals 0. I still have work to do to calculate what C1 needs to be. Notice that my second initial condition is in terms of the derivative of the solution. So let me back up to my general solution and calculate its derivative. Now we're told that if we plug in t equals 0 into this derivative, the output should be 3. So the algebraic process will be very similar to what I just did when I plugged 0 into my original function. So let me give that a shot. So those algebraic steps indicate that C1 needs to equal 3/2. So I started the problem knowing the general solution, the infinite family of functions which satisfy this differential equation. Now, in addition, I can identify one specific solution, the actual solution as our author calls it, which satisfies the differential equation and which also satisfies these initial conditions that were provided. Let me scroll down and write my final solution. So here I have my final solution with the two coefficients plugged into my general solution. All right, that wraps up section 1.1. Please email me or visit me in office hours if you have any questions.